Okay, let's differentiate the function y equals 2 to the power of x. Of course, this is an exponential function, but unfortunately it's not base e, because remember, the only exponential function that we've dealt with so far is, of course, base e. Remember, the derivative of e to the x is pretty simple. The simplest thing of all in calculus, the derivative of e to the x is itself e to the x. So remember, the tangent slopes are the same as the y values of that function for all x values. So there's one quick recap, and another item we'll need in this example is differentiating not e to the x, but a stretched e to the x. So what if we have something like the number 4 in here to go along with our x? So remember, if there's a 4x instead of an x, that's a horizontal stretch by a quarter if you're keeping score. In terms of derivatives, that would require us to use the chain rule here. So we have a trapped function. So again, another way of decoding this when you're differentiating is to see you have a linear 4x trapped inside of an exponential, which of course is a composite function, which requires the chain rule, which is the derivative of the outer function, which is derivative of e to the power, which is a simple rewrite, and not just e to the power of x. Remember, you have to trap that 4x in there as well. So just say to yourself, rewrite that. I've dealt with the derivative of the outer function, and then the derivative of the inside function is what we need to finish this off. The chain rule, of course. And the derivative of 4x, since that's a linear, is just the coefficient 4, which we'll write in front. So the derivative of e to the 4x is 4 times e to the power 4x. So you're probably asking yourself, how does that help us here when we don't have a base e? Well, we can get rid of that 2 and replace it with the base e, and then we can use this information over here. Just some previous knowledge, hopefully. So I better rewrite this whole expression first. So instead of 2, put brackets around that base. Instead of 2 to the power of x, we're going to try to get a base e in here. And in the previous video, we looked at if you combine a base e exponential with its inverse, which of course is ln, and not combine it in any way, but compose them, put the ln inside of the natural log, they wipe out each other. So think of the input on that natural log as being what this confusing expression is equal to. And if that's confusing, you might want to rewatch the previous video. Excuse me, or simply just check on your calculator, type in e to the power of ln of 2, and you will maybe surprisingly see that it's just 2. So believe it or not, that is equal to that 2. So now we can just use our exponent properties and recognize that if we have something, a power raised to another power, we just have to multiply those two exponents. So no calculus yet, believe it or not, but we're getting close. So this is going to be ln of 2 multiplied by x, and that's all in the power trapped inside that exponential base e. Now this situation is pretty much identical to the e to the 4x situation, except we don't have a nice round number 4 as the coefficient on x. We have an irrational number here, ln of 2, which remember is still just a number, it's a constant. So if we differentiate this now, we just use our chain rule. So we differentiate the outer e, and all that is going to be a simple rewrite of that function. And to finish off our chain rule, we have to multiply by the derivative of the inside function, which is a little more confusing than the 4x, but it's ln of 2 times x. The derivative of that is still that coefficient, that constant, ln of 2. So our derivative here, if I can squeeze this in here, is going to be e ln of 2 times x in that power, multiplied by the coefficient on that linear expression, which is just ln of 2. And so this goes back to, I guess, our original form here, which was base 2. Remember that e ln 2 times x was just the same as e ln of 2 raised to that power of x. Well, this is just equal to the 2. Maybe a little more coherently, we'll write that out so you can see what I'm talking about. If we pull this thing apart again, we could say, well, this is e ln of 2. We'll pull that apart and then apply that other power. And of course, if we multiply those powers, that's the power raised to another power. We're kind of working backwards to finish off this derivative. And of course, we recognize that that is just the number 2. which is usually what we do when we're dealing with exponential derivatives. You try to go back to the original base that you were dealing with. In this case, it's base 2. So there's our derivative. It's 2 to the power of x times ln of 2, and you can write it that way. Of course, might be slightly more common to say that's ln of 2 multiplied by 2 to the power of x.